Turn on stream. You should know that I am waffling. And the specific manner in which I am waffling is as follows. I have, I think, some well-formed anxiety about what to do on Wednesday. I would like you all to be able to implement Edwards Curve digital signature cryptography with Curve 25519 in Rust this week. To me, this seems reasonable. I don't know that it will be easy. I don't know that it will be particularly hard. I'm not going to necessarily encourage you to use your IX, which I expect to be slow, because it is very hard to make IX fast. So you can use someone else's IX, but I would like you to at least have an awareness of what is going on inside of the ones made in industry. So, next term, the thought is that those of you that would like to continue will implement your own operating system. You're not going to install that on your computer and use it for the rest of your career, right? You're just going to have some sense of what it is. So, implementing things to see how they work. And perhaps you did this in data structures or something like that, right? Okay. So what am I anxious about? Basically, the way ED25519 was introduced into the world is someone wrote it in Python and then published it and said, don't do it this way, it's too slow. So we're going to do it the don't do it this way, it's too slow, because the fast way is out of scope of any class, not just this class. So, okay, so I got the Python working. It was written in Python 2. It took forever. I wanted you to maybe get that working in a lab. Giving you a Python lab for the entire 90 minutes seems kind of silly. But also, we're a little bit behind. If we think back to last Monday, we were in the thick of the numbers lecture, which is this one right here. And I sort of didn't finish up numbers, and I wanted to give us a little more context on that. So I was going to start at slide 52 of numbers, get to the end of the numbers lecture, start the EdDSA talk today, probably not get to the end of that, and then finish that talk on Wednesday, and then give you the Python version of the Rust assignment, which is just to get Python someone else gave us working. It's not ludicrously complicated, but it doesn't work out of the box. And then the homework is get that Python to work in Rust. And it will be faster, but it actually won't be that much faster because the things slowing it down are algorithmic challenges. So that's the plan that I have right now. And wow, this lecture is already showing up here. That's crazy. So that's the plan. Okay, what happens with that? Once that is done, we have a little bit of graph theory, and stacks, lists, and trees are all graphs. So we'll introduce the stack and the heap because it's useful. I'll make you implement a list and a tree in Rust because, you have to implement something in Rust. Why not a binary search tree? Then I'll ask you to implement Dijkstra in Rust because then, oh, you've implemented an algorithm in Rust. We're just checking boxes, right? Then at the end of all of that, we'll do the version control system. And mostly that's going to be how quickly can we get that assignment out so you can start working on it, and then we'll just do basically bonus lecture content for classes there. So there'll be, I wasn't planning on doing more in-person labs. So also the other thing that's going on this week is we're starting to fade out the lab to get more lecture time as we get later into the term. In theory, you've had time to hack on Rust while I'm around to help you now. I haven't been getting a lot of questions, so we'll pivot a little bit back to lecture. Okay, so that's the plan. If you have questions about anything, let me know. How is IX going? Pretty good? Okay, cool. It seemed a lot more manageable. Has anyone done division? You got division working? Have you submitted it so I can look? Yeah. Okay, cool. I'll take a look. Well done. These slides will be less interesting because they're meant to help you with division. So all right, let's get cracking. Oh, so I didn't know this. There's a piece of software named GitKraken. Have you heard of this? I can't tell if they're making fun of us or we're making fun of them. But someone's getting made fun of here. And I have no idea what it does, right? See, it's even a frequently asked question. It provides I don't know. Very strange. So anyways, be careful when you say get crackin'. Okay. So here's our motivating example. Let's back up a little more. Okay. So last Monday, I stood in front of you and I talked breathlessly about numbers, which again I do love. I love numbers more than people. And I talked about how sad it was to me that my computer didn't have numbers in it, but it just had bits that were pretending to be numbers. We probably all remember this. But sometimes you want to use your computer to do calculations on numbers, so you have to either program the computer to know what numbers are, or just hope that you don't use any feature of numbers that the computer doesn't already know about. Both of these things are kind of sketchy, and they don't come up that often, but if you're a computer scientist, you should know about them, okay? So my claim was that addition and subtraction at infinite precision are pretty easy. They're not like the easiest thing in the world, but there's nothing necessarily algorithmically interesting about them. You sort of just line up the digits, compute down the digits, and you do carry bits. And that's all. That's all you have to do. So it's a relatively simple problem of adding things together, seeing if there's a carry, promulgating the carry bit to the next location, and then performing an addition. Now that means you're dealing with like 3 arguments at a time and stuff like this, right? So like you have to write the code correctly, but there's not an algorithm that is causing you problems. Multiplication at least requires one leap of insight, which is you somehow have to deal with the fact that any digit in a multiplication can affect any other digit. Basically, it is much closer to SHA-256 in that sense, where changes to one digit can show up anywhere else in the solution, within reason, right? And it's highly predictable versus SHA-256. And then division is markedly more complicated and has been left as something of a challenge problem. And division and modulo are the same thing. These things are just Euclidean division and Euclidean remainder, so there are names for them, but we don't have to call them that. I used this motivating example just to show sort of a long multiplication, which I want to build up to. And this is based on the people I assigned RSA to, which is not the cryptosystem we're learning this term. But 14 of them were at MS level. The MS level classes are 4 hours per week for 14 weeks, which is a different shape than your semester. And because I am entitled to 2 to 3 hours of your time per 1 hour of class time, that meant for each of those 4 hours per week I saw them, they owed me 3 to 12 hours of homework, which none of them provided, and that's fine, I'm not mad, okay? And then there were 34 undergraduate level, BS level computer scientists. They were experiencing, as you did, 3 hours of instruction per week for a 15 or 15 and a half week term, depending on how you count it, right? Since I am entitled to 2 to 3 hours of your time outside of class for 1 hour in class, that meant that I got 6 to 9 hours per student per week in that class. And I was trying to figure out how much time I wasted last term, right? Which was a lot. It was a very large number. So I don't know if you care about this, but like I ran a 50 miler this weekend, and I got a report from Garmin that I spent 24 hours in the last week running, which is like, that's an entire day. That's like more than a part-time job.
That's a seventh of your total time.
Yeah. And I was like trying to figure out why my knees hurt. And I was like, oh, it's because I'm stupid, right? Like my brain was supposed to prevent me from running before I did that. But it didn't. My brain didn't work at all. It was like, you can go faster the entire time. And that was wrong almost the entire time. I could not go faster. So speaking of my brain not working, how many of you can multiply 3 two-digit numbers times each other without making a mistake? Go ahead. What's 14 times 12 times 14? Good luck. You're going to get completely owned. You will definitely transpose one digit by accident. Like, even if you can do that mathematically, there's also like vision challenges, right? Like making sure you read the correct numbers and stuff, right? So as a rule, humans are not particularly good at this. You can definitely train to do it, and some people can do it innately. But as a rule, people can't do 14 times 12 times 14. That's pretty hard. That said, I can do 2 of them pretty easily, right? And how do I do that? Well, I essentially model out how I would algorithmically introduce multiplication in my mind. So, what's this looking like? Well, I do 14 times 12 in base 12, And one of the reasons I wanted to point this out as an example is in the computer, you're probably going to be doing multiplication in different numerical bases, right? So I think many of us are familiar with, I'm wondering if my legs are strong enough to stand up. I'm going to go with no. Paint Online. Perfect. JS Paint. Even better than MS Paint. Wow, the internet. Thank you, Al Gore. Okay. We don't thank Al Gore enough. That's what we don't do. We're imagining that I'm drawing on a whiteboard because I'm able to stand up, right? Which is false. Is this the pen? Okay. And so, oh no, my mouse is teleporting? Okay. Is that, can you see that at all? What if I make it red? Oh, that's pink. Is this red?
I'd call that more of a magenta.
I think the red is harder to see.
Yeah, this is not it at all. Okay.
Try to brush things.
There we go. And we don't like the red. We like black. Okay. So we can also multiply 14 by 12 as follows. So perhaps you've done this at various points in your life, and you've said, oh, look, it's 1 times 1. That's 1. This is 1 times 4. That's 4. This is 1 times 2. That's 2. And this is 4 times 2, which is 8. And then, depending on what year you went to school, you'll maybe have been told to connect things along the diagonal. And this is going down. Let's see. 1, 6, 8, right? Because the sum of these is 6, that's an 8, and that's a 1, right? This is an array operation, right? So the way you determine the digit significance of a product is this is in the ones place, and this is in the tenths place, so it goes into the tenths place. This is in the tenths place and the ones place, so it goes into the tenths place. And then you just do a summation of the powers, right? This is one way you can visualize the multiplication. Do computers do this? No, of course not. They don't know about base 10. So, what is the claim I'm making? Oh, I'm in the same browser window. What is the claim I'm making here? Well, perhaps the example I have is maybe we can think of this in base 12, right? Like I don't know if you think of things in base 12, but like maybe you should. And so if we think of this in base 12, what do we have? Wait, can I do? Okay. If we think of this in terms of base 12, well, how many 12s do we have? Not too bad, right? But this is 12 squared plus 2 additional 12s, right? So we have a 1 in the 12s place, and then we have a 2 in the 1's place, because this is 14 is, I'm going to use n, 1, 2 in base 12. Okay. Then separately we have a 1 and we have a 0 because, how do I spell because? 12 is on 1, 0 in base 12. And then we can perform the same multiplication. So we have 1 times 1, which is, that's just 1. 1 times 0, which is 0. And then we have 2 times 1. Now, this 1 represents a number of 12s, but we just put a 2 there, right? So how do I think of this? This is now 12 times 12. So if we sum up along the diagonal. That is 12 times 12 plus 2 times 12 plus 0 times 12. So that is 12 times 12 plus 2 times 12 plus 0 times 1. And so this is represented to me cognitively as 144 plus 24, which equals 168. What am I trying to impress upon us here? The numerical base with which you make these calculations is not relevant to the ultimate numerical correctness of the calculation, which means that if you're accustomed to thinking of things in terms of digits in base 10, or bits, or digits in base 12, or digits in base 16, or whatever you want. What do we call the hexadecimal digits, like hits or something? Hexits?
I think hexes.
We're going to call them hexits, right? It doesn't matter, you're going to get the same numerical result, right? So when you're working on your multiplication, I found it much easier to just think of it in an arbitrary base. And I'm going to continue with the slides representing this sort of arbitrary base, right? So this is an example of a base 12 computation, right? This is an example of a base 10 computation with an error bar, right? Okay. So my claim was that 34 times 139.5 is not that easy. I think this is more bits than most people's brains handle comfortably. We have 4 digits times 2 digits here. This also doesn't seem to neatly line up with any particular numerical bases, right? 139.5 is like not super evenly divisible by anything. So you could have approximated with 140 times 34. I don't know. That's not necessarily trivial either. You're still doing 14 times 34 there. But we can express this digit-wise. And I did this by breaking out each of the digits. And I am using base 10 here again because, like, what other numerical base am I going to use? Does it even matter, right? So I'm doing 1395 times 34. So how am I going to do this? Well, I do the same operation I carried out over here in JS Paint, right? I populated my table. I have 1 times 3, 3 times 3, 3 times 9, 3 times 5, and so on, right? And this, like, pretty quickly leads to some, like, relatively enormous problems we didn't get when we were multiplying things relatively close to 10 times each other, which is that, like, this number has the wrong number of digits, and I'm going to have to figure out the digit alignment problem. So, for example, let's see, how do you do screenshot? Ooh, I don't actually know if I can do this on Linux. Okay, I might need a Linux. Are there any Linux power users in class today? No. Okay, we're cooked. We're fine. Okay, so we still kind of want to do the same alignment thing. I'm going to pivot to, my inclination is still to use red so it shows up. I'm going to try blue and we'll see if that's visually working. And that,
No.
can we use a chunkier line? Is that okay?
That's
Yeah.
better.
Should use red.
Now we want red?
Well, red shows up well against black and less well against white.
Well, the problem is, wait, no, wait, I might be a genius. Hold on. Everyone get ready to sound the genius alarm if this works. Where's Phil? Okay, all right. Red shows up well, we agree? We all agreed? We're speaking now or forever holding our peace, right? Okay, and so I think we can line these things up in this manner, right? And so this is going to give us numerically, and I think we'll start with the, oh no, is it going to make the background white? Okay. So this is going to end with 2, 0. Wait, no, show up, 2, 0, right? But this 2, 0 is going to be 1 bit less significant than the 36 plus 15. So really, what we need to do somehow is we need to denote this 2 and 0 as separate. So we need to do 0, and then we need to do the higher order bit of this one and the lower order bit of these two. So we're going to have our last digit will be 0, but our second to last digit will be 6 plus 5 plus 2. And oh, that also has a carry. So even though this is trivially 13, right? We're going to get a 3 there, and then we're going to have to carry an additional 1 over to the next column, where there's a 3 and a 1, but also the low order bits of these 2-digit values, which are 2 and 7. So then we have 1, the carry bit, plus the 2 and the 7, plus we also have the 3 plus the 1. And at this point, are you like pretty sure you want to use a computer to do this? Right? But we're dealing with a bit, byte, or numerical alignment problem where lower order numerical values, both their carry bits and their higher order bits, so they're multiples of 10 or 16 or 256 or what have you, are also going to spill over into the higher bin. So this is 4 with a carry bit. And then the next thing. So maybe this ends with 430. I don't know. And actually, where's my terminal? We can check. What am I doing? 34 times 139.5. And it ends with 430. So in fact, we did get the correct trailing 3 digits, right? Oh, that means we should have kept going because it was about to get really easy. Look, because these numbers are easy to find. I'm sad. Okay, we could have really crushed there. Sorry, I have to clean this up. I'm gonna delete it in a sec, anyways. But oh no, it's awful. Oh, I don't know how to use Paint. Okay. Oh, it's disgusting. Okay, close. Quick. Okay, we escaped. I think this one should be preserved for posterity, actually. Hold on. Screenshot. Wait, maybe I can just wait. I have an idea.
Yes.
Well, I want to get it in Discord. Does this work? I'm unwilling to install Discord on Linux. It just feels wrong to me. Oh, it's pumpkin themed. Which, are we this class? No, oh, it works. Wow, so cool.
I think the compression saves the white squiggles around the numbers.
So the moral of the story is never have information density. Okay. Which was what we learned from F-16, right? I just think it's so impressive that the Navy named one of their airplanes after the number. Okay. So, for my money, this is what I just showed you. I don't know if we agree with that. But we can sum this up. That was the 2, the 5, and the 6. And those were the 2 and the 5 and 6 I wrote out. Then there was a carry bit, a 1, and a 1, and a 3, and a 7, and a 2. And that adds up. And that numerically gives us the entire value. Now, we're toggling back and forth between these slides. Why are we doing that? Well, we want to represent that this same operation we did over the arbitrary numerical base, in fact, can be expressed algebraically over an arbitrary numeric base. And so here, I was implicitly doing everything in base 10, because I was working with decimal values and I was breaking them up by digits. Well, I can express that precisely and mathematically by saying, well, this value, if I set it up as single digit precision, scientific notation, summations, right? So I have a 1 times 10 to the 10th, 10 to the 2nd, 3 times 10 to the 1th, 9 times 10 to the 0, and 5 times 10 to the negative 1th. All of these 10s, well, really, what this has actually turned into is a polynomial expression, right? And I'm going to try and do something extremely obscure, which is I'm going to attempt to express this with symbolic computation. I just taught myself symbolic computation because I thought it was important. So we'll see if this works. I'm going to set x equal to sympy dot symbols x. Okay. And then what am I going to do? I'm going to get this out of full screen and look at it. And I'm going to say, well, I want there to be some expression which is going to equal 1 times 10 squared, or 1 times x squared plus 3 times x plus 9 times x to the 0 plus 5 times x to the negative 1. Oops. And I can look at that expression. and this is how it is expressed symbolically in my favorite symbolic computation engine, which is SymPy. There's some physicists in here. Do you all learn SymPy? Have you seen it before?
We've used a little bit. But
Okay.
not much.
Does anyone use either Sage Math or Mathematica? Do you use Sage?
Yeah, Sage.
Okay. I don't know how to do this in Sage, but like, send me a Discord to maybe do this in Sage next year. Okay. Okay. So I can take this value, and this value represents 139.5, but I can create another one. Let's take expression 2, which is going to equal 3 times x to the 1th, or we'll just say x plus 4. It's expression 2. I can multiply expression times expression 2. And I think I can simplify this. Okay. That looks kind of heinous.
I'm not sure that's better.
Yeah, we don't have the... Oh, this is as simplified as it can get until we plug something in, right? So, what is the problem we are trying to solve here? Well, because we used digits, we have to be able to relate this back to some numerical base somehow. So I'm going to do that by taking this expression, and I am going to substitute x for 10. And that's going to give me actually the numerical result I wanted, which I don't know, is probably on these slides somewhere. Well, it has to be, right? Because we found there was the 4-3 at the end. So this is the same way to figure out the numerical result here. I am expressing it as a polynomial, and I am substituting in the base as the x value in the polynomial. What's going on, though? Say, for example, this was expressed in hexadecimal. We can actually still do the same calculation. We just input a different base, and we'll get a different number back. And you might be skeptical about that. That's pretty reasonable. But we can pretty much check this. I don't know how to put in decimals and hexadecimal notation, so I'm just not going to try. That's pretty close. 651, 69 divided by 4. Like, yeah, those are like kind of the same numbers, I think. I don't know how close they are. So whatever your numerical base is, you can still express it as a polynomial. You can still express it algebraically. And being able to think of this as a polynomial or algebraically means you can begin to use arbitrarily sized integer fields in order to express your numerical results. So this is cool. Do we all agree this is cool, or is this boring because it's math? Okay, you think it's cool. Is there a second person? Can I get a second for the Oh, there's some thumbs up over here. All right. This side of the room, a little less energy today. That's okay. I still respect all of you equally, right? I just want to be clear again that you are all number 1 on my list of the favorite student rankings, and it's not a 0 indexed list, right? It's a 1 indexed list, right? Okay. So, I did show this to students in the past, okay? And they all hated it, right? So I have saved you. I have solved this problem. You never have to think about this ever again. All you have to do is do this thing, okay? It's super easy, okay? So it is banned for people that have taken this class to be stressed out about algebra. So algebra is trivial. You just type it into the computer, right? So you're not allowed to be scared of this anymore. And I mean fake algebra. I don't mean like the real algebra they teach in the math department. I mean like what I took in 7th grade or whatever. Did you all take a class called algebra in like either middle school or high school? I'm making this up. And there's like 2 of them, right? There's algebra and algebra 2. Okay, yeah. So, right. I thought maybe you learned this in like around 8th grade. And I don't know if I think it's in 8th grade because I remember 8th grade or because there was a movie called 8th grade that I saw once.
I think it's like 10th grade.
We think it's like 10th grade. So I guess I was a genius that was 2 years ahead of grade level.
Or no, that might be like algebra 2 or something.
I think we should go with the me being a genius hypothesis because I liked that one. Okay, but okay. I don't know what you learned in high school. I also don't know what Common Core is, which is going around. So
It's terrible.
I tried to teach you this in a way that doesn't assume you learned anything in particular in high school. So hopefully that worked for you. And if it didn't, check out this tool, import SymPy, and you're good. Okay. So if I have 4,096-bit integers, or 512-bit integers, or 256-bit integers, which are the integer bit sizes that I've seen use of in cryptography, oftentimes we're going to want to express this as a polynomial over 64-bit integers, or more commonly in my case, I did them in 32-bit integers and then stored the results in 64-bit integers. Whatever you want to do. You're going to have to deal with overflow. And what was overflow? Overflow is the thing where I got an expression that pretty quickly had 5 terms in it, even though I was only multiplying 2 numbers together, right? And that was emotionally exhausting. It really took a toll on me. I was quite sleepy after doing all of that, right? So how are you going to deal with this problem? Well, if we look at this numerically, if we're operating in base 10, we are in big trouble, because this requires 2 bits of precision in base 10, or 2 digits of precision in base 10. This requires 2 digits of precision in base 10, and so on. So when you multiply 2 one-digit factors together, you might get back a 2-digit product. What this means to me is if I multiply 2 U32s times each other, my result I get back is unlikely to fit in a U32. In fact, it fits in a U32 at probability 1 over 2 to the 32nd, right? It is very unlikely that when I take arbitrary bits, I get that numerical result back, right? So one way to deal with this is to take your U32s, cast them into U64s, so they're necessarily not using all of those extra digits at the top, multiply them together, and then cut that U64 in half somehow. The natural way is to take the modulo, 2 to the 32, and then also the division by u to the 32. And now, by the way, you're having to do division. Great, right? And you split that up and you can put those back in U32s. And so if you have a vector of U32s, you just have to put them in 64s, multiply them together, cut them in half, and then put them back in the correct position. And that was exactly what I showed right here. This is showing how you figure out what index, last, second to last, next to last, within your sort of vector of digits, each one of these numerical results goes into. And actually, there is still, wait, is there a bunch, there's a bunch of like white dots?
I think that was there already.
Wow, JS Paint, garbage. Yet somehow still better than MS Paint. Wait, there's extras? There's a head tracker? Allow. Okay, start. Ah! What'd I do? I don't know what it's doing. Oh, it's looking where I'm looking. Okay. Oh, I can't just move my eyes. I have to move my head.
It's called a head tracker.
Oh, this is not okay. And then so, can I? Oh, I think when you blink, it does inputs. Okay. I don't know what we're doing. Stop.
Something very cool.
One of you has the homework assignment of figuring out what I just did. Okay. Okay. So, you have 2 integers with 8 bits of precision. You multiply them together. What's the largest number you can get? Pretty easy. I'm going to take 2 numbers with 8 bits of precision. I'm just going to pick the biggest number I can fit in 8 bits. What is going on out there? Is it fun? That's like kind of a fun siren. Oh, it's a fire siren, not a medical siren.
Oh, okay, yeah.
Yeah. So I think we all love having 8 bits of precision. So we take this number, which is the 8 bits of precision number, store that in x, multiply x times x. It's kind of an oddly large number. How long is that? Well, it's this big. Is that right? Is that for real? Does anyone know binary? That's 4. That's 4. That's 4. Okay. So, wait. Oh, I only typed in 7 ones by accident.
Oh.
Okay. This is what I get for not using hex. Okay. There we go. Okay. Is that right? Yeah, okay. So, what is the bit length of x times x? Does this work? Okay, right. So if I multiply two 8-bit numbers times each other, I potentially need 16 bits of information to store them. Why is that? Well, because there's 2 to the 8th different numbers, and I can multiply them all together, so that's 2 to the 16th possibilities. It's just 2 to the 8th times 2 to the 8th. It's the same. You can think of it in terms of probability. You can think of it in terms of area. You can think of it however you want. You need twice as many bits. You do not need twice as many bits when you're doing addition, because this thing just has a bit length of 9. So when you add things together, you have a carry bit or a carry digit. When you multiply things together, you have a carry as big as that number is. So look out for this. Deal with it however you want. So here's just like my executive summary. Multiply chunks of at most half the size of your biggest integers. Keep track of the significance, which is their scientific notation in whatever numerical base you're working in. You're going to get a bunch of numerical values at every single significance. And you're just going to have to perform adds over those terms. And so when you add them all up together, then you're going to be calculating what each digit in whatever your numerical base is. Okay. For division, here is my recommendation. I aligned the highest digits. So what does this mean? Oh, I was having fun with JS Paint. I'm going to open it again. Are we all JS Paint appreciators now?
No.
No. I'm just going to pretend I didn't hear that.
Oh, I'm concerned about its functionality.
Oh, no, wait, no. We need juicier lines. Do you all know what cerebrospinal fluid is?
Isn't it like isn't its name pretty accurate?
It's like, it's brain juice, right?
Yeah.
It's probably what zombies crave. But anyways, I was talking about cerebrospinal fluid last class, and some of them seemed to know what it was. I was very surprised by this. Because I didn't know what it was, right?
Oh.
Yeah, I feel like that's a thing that people know about.
Cerebrospinal fluid?
Yeah.
Does it, like, come up in a class?
I don't know.
I just feel like it's pretty self-explanatory.
Yeah, it's kind of in the name.
Your cerebrospinal.
It's nice that you... Oh, this is a difference from MS Paint. Do you see the text box occluded? I'm going to refer to that as cringe. Okay. Okay. So then we're going to do 139.5. Okay. So how do I think of how to do this? Well, I imagine the good old long divisions. We all love long division, right? We all love long division, right? And so what do? Step 1 is you align the most significant digits. Okay, so I align the most significant digits and I say, okay, how many times can I divide 13 by 34? And the answer is 0. So we go ahead and we toss a 0 up here somewhere. Or like, I don't know how to do long division, right? Can I get this back? No, okay. Undo, okay. 0. Okay, so we have a 0. And then what do? Well, then we have to move this down. That's not what I meant to do. Using MS Paint is hard. So we move this over, and we align. What are we doing? We're aligning, and we're no longer aligning the most significant bit, but we kind of are because we're thinking of there as being a 0 here or whatever, right? Yeah.
But you need another 0?
Well, it's a leading 0, right?
Well, wouldn't there be 2 initial zeros? Because 34 doesn't come to 1 or 13.
Oh, that's reasonable. Yeah, so 2 leading zeros. So just imagine there's 2 leading zeros then. Yeah. I think what we should actually imagine is there's probably no leading zeros. So I'm going to delete this. Okay. Okay, and then what do? We have to see how many times 34 goes into here, which I'm guessing is like 4. Because okay, I happen to know that 34 times 4 is 136, right? So what do? You take your 136, and so on. Okay, so this is what I'm imagining when I say align the highest digits. This is what align the highest digits mean. Find the first thing that you can actually divide by at all. Okay? That's align the highest digits. Then you divide. I divided 139 by 34, and I got, what was it, 4 times 4. I kept track of significance. So, after I did this calculation, I got back, I'm just narrating long division. You know how to do the long division. What I'm providing is the commentary on its relevance. This is going to be 003, and we're going to have a 4 up here, right? So 4 times that is, so the leading digit is going to be 4, okay?
Is that smudge on the projector screen?
Where? This?
To the right of the 003.
To the right of the 003. Yes. Here, let's demonstrate. I'm going to select that area.
Oh, yeah.
And then I think when I delete it, the sludge stays there. So it's not part of the screen. Okay. So we need to keep track of the significance. And what is the significance here? Well, because we aligned at the ones bit digits, this is actually exactly precision of 1. So we can do point something. And I think the point we can do is this is 0.1 because we're left with 35, 34. And then we're going to have some very small number because we have 1 divided by 34 after that. So by keep track of significance, what do I mean? In sort of conventional division, that would mean where you are in relation to the decimal point. You can also think of this in terms of scientific notation. What is the power of your base times which you are multiplied, right? And so this is 10 to the 0. This is 10 to the negative 1. Okay. The final remainder is the mod, and my final remainder here is whatever it is, 35 something. Okay. So those are the arithmetic operations. That was kind of fun. The next stuff is not like really particularly slide heavy, but it's philosophically heavy, which is that one of the takeaways I was hoping would sort of come out of this assignment is thinking a lot about function types and the types of functions you kind of need to work with or don't need to work with. When we did this in my preferred language, the C programming language last term, we actually had a different function signature because there was no graceful way to return a data structure from a function. There was a way, it wasn't graceful. In Rust, it mysteriously becomes graceful because you can pass around data structures of arbitrary size. Okay, maybe this is not graceful. You can pass around data structures of arbitrary size if you correctly use your borrows. So my suggestion for an implementation decision on how to do this, and this is enforced by the autograder, but you shouldn't think of it as being enforced for any reason other than to give you an automated testing script. If you implemented it in a different manner, that would be completely correct and reasonable to do. The only reason I restricted you is to give you some help on the assignment. So I recommended this usage where you pass borrowed values, right? So this is not actually the value A. This is giving someone permission to look at A. They cannot edit A. They can only perceive A. And the same thing is true with B. And then out of the ether, you conjure a new data structure, which is this IX type, and you return that data structure. Now, this costs money. And specifically, it costs money for all of the bits you have to buy to store that data structure. But what does Rust do? Rust makes it so punishing to work with data structures more than once. You're going to be throwing these things out all of the time. So this function prototype is meant to be very similar to a function prototype where you pass 3 arguments. A and B, which you add together, and C, which is a data structure you would provide that you then populate. And it would have to be a mutable reference. Right. So this is kind of goofy, but this is meant to be similar to the x86 assembly add instruction, which is documented in a variety of different places, none of them particularly easy to look at. And so in computer hardware, when we actually perform operations of this type, what you generally provide is not numerical values, but the locations of values. This is a location of a value. This is not the value itself. This is telling the computer where to go to look up that information. Okay? And then, if you're just providing the locations of 2 values, what you could additionally provide is the location of a 3rd value where you store the answer. So instead of returning an IX, we could think of this as getting a 3rd argument that is a mutable reference to the data structure that contains the solution. This is a computer architecture topic. It happens to have come up in the implementation of this assignment, so I wanted to point it out.
So using a somewhat static memory location for return value, kind of?
I just say user defined.
Okay.
Yeah. It can be on the stack or heap, it doesn't matter. But you have to have enough space. Well, no, it can't be on the stack because it's potentially infinite size. Or I guess it can, and you can just encounter, you can panic. Okay. Why do we have to borrow these? You have to borrow these things because they're not numbers. They're data structures that represent a number. They have to be a data structure because they're infinite precision. We don't know how big they are, so they have to store their size. So we have to put them somewhere in the computer, and this has to be sort of an abstract, vague place. This is teasing a future lecture. But some of these things we can't put anywhere in particular. It is much more similar to, and this is not how it would work in Rust, right? But it is much more similar to having a vector, and the Platonic ideal of a vector, not a Rust vector, but just the notion of a vector, where you store each digit and its significance independently, and that is a data structure. That is not the same thing as a number, right? On this assignment, where I recommend you do things this way, question, is there a way to use just plus and minus? And the answer is yes, with a quixotic note in it, right? Because what would it mean to overload addition to work on data structures, right? I think this is horrible. I think we did 10 times or 12 times 14 earlier. It is, I understand that Python wants plus to be allowed over these arrays, but that's extremely weird. Multiplication just obviously isn't allowed. So you can take the Rust programming language and you can program it to understand what plus means in the context of these taking 2 IXs and adding them together, right? But it is fundamentally unnatural to do that for a few reasons. The first is my recommendation that you use borrows rather than throwing the number in, because otherwise, if you don't just borrow this, you never get to use that variable ever again. Someone else gains access to that variable; it's not yours anymore, right? So, if you're doing that, now if you're adding these together, you can't use borrowed copies of them, right? Or maybe you can do it with a macro. I don't know. That sounds unappealing to me. So you can set up plus and minus, but probably what you're going to end up doing is being wow, I have to put in borrow marks everywhere, and I can never really save the return results of my computation. So it's really weird, really fast. I looked at it. I didn't like it as much as this. Teddy looked at it and hated it. So like, I'm just like not recommending you do this. I think I will like maybe give you some sample code showing you how you can do it, and you'll like look at this code and be like, oh, that's so much worse than just using function notation. Or maybe you won't. But it will be very easy to figure out how to do this if you want. It's called traits. Just Google it. But I would not use them. And anyways, that's what I taught you last Monday. You all remember me doing that last Monday? Okay. Thankfully, we didn't use more than half of class time today to finish that lecture. Okay. Now for the good part. So, wait, how do I not have
Now it's
EdDSA
like
open?
last time, I think.
That's not my fault. There's probably just like not going to be a lab on Wednesday. That's okay. Will there be a... We're going to see where we get today, and then I'll make an assessment about the lab. But there's more content to go. Okay. Welcome to Systems in Rust. Welcome back. You may remember last Monday when I talked for 40 minutes about multiplication and division. And you all had to sit there and listen to it. A midterms verbal update is down. I started looking at the midterms. They seem pretty good. I think what I'm going to do is like, if there's something wrong with yours, in my view, I'll send you a note saying what I think is wrong, and otherwise A+. So that's what I think is going to happen. Again, there's this like very strange thing going on this term where like, to me, it just like feels miserable to write Rust, and then like the first time you run it, it just works, and you're like, oh, I thought I didn't like programming in Rust, but now like the hard part of programming, which was debugging code that I wrote, like doesn't exist anymore. So it's like easy. It's very strange. So to me, looking at your midterm code, I think this happened to all of you. Where like I think you were just like writing code, and it's like the worst code you've ever seen in your life, and then you test it and it's perfect. And you're like, guess I'm done. Like I have nothing else to do. I've done like so. I imagine that's what happened to you. I don't know if that was the narrative you felt, but that's consistently what I felt with Rust, where I just like write something, I'm like, finally get the borrow checker working, like the compiler stops yelling at me and it just works exactly the way it's supposed to. I find this very strange. It has completely removed the joy of programming from me. So I'm going to become a mathematician, as you've noticed. Keep at working at the arbitrary sized integer. Does anyone have any questions on the homework at all? Anything you want to talk about? Okay. I think it's a great homework assignment that builds character. Once we're done with that, that unlocks the last and greatest of the cryptographic homeworks, which is what we're covering today. Today, I'm going to introduce private key cryptography. What does the private and private key mean? You know what, I guess we'll call it like shared key cryptography is, which is Enigma. So in the Enigma machine, everyone that has the Enigma machine agrees on how you program the machine. You type something into Enigma, gibberish comes out, you send it across the Atlantic or whatever they were doing. They type it in their machine and you get the answer back. And so that was covered in CS1, and if you're worried about it, just imagine a rotational cipher where you substitute every letter for the next letter in the alphabet. It's exactly the same. Public key cryptography is different because when you have shared key cryptography, somehow you have to share the keys. How do I share the key with my credit card company? Right? Like, there's no graceful way for me to contact them. I can't like get on a plane and go to Manhattan every time we need to do a credit card transaction, right? So somehow we have to do this in plain sight over the fundamentally unsecure internet, because it is also impossible to secure the internet, right? So that is private key cryptography, and it solves the problem of, can I buy something on Amazon? So there was a lot of money in getting a solution to this problem. Separately, not very long, I think like probably by the time the first private key cryptographic systems were discovered, people were already using them for digital signatures. Digital signatures is solving a different problem. It is not the problem of how do I transmit this secret to someone so that no one else can see it. It is, how do I post something on the internet that everyone knows came from me? So I need a way to sign something, and it can be verified that I created it. There are two, at least that I'm aware of, solutions to the digital signature problem, and the one that is ascendant right now is the Edwards curve digital signature algorithm, EdDSA. It is monumentally mathematically interesting in a subfield of mathematics that I don't care about, which is unfortunate for me. And it is massively, massively interesting in hardware security, and I don't know how to teach that part of it without doing dramatically more architecture. So the plan is, if we run into the end of the slides today, I'm just going to give an impromptu talk about side channels. And they're cool, but we have loaded up at the tail end of the term. These are the side channel attacks, so we're going to teach them once you have something to chew on for a while. We'll go back and talk about side channels, and I hope it'll be covered well enough that it makes sense to you. So Edwards' curve solves the problem that we haven't introduced yet that we're going to introduce later. Public key cryptography. My voice is dying. This is a problem. Okay. I'm trying to hit a target volume. Am I louder than I need to be? Can I talk this loud and you hear me okay? Is that okay? Okay.
Yeah.
I'm also not used to talking sitting down. Okay, I'm going to be, I think, a little quieter, and I'll try and keep watching the back of the class and just flag me if I'm getting too quiet. Okay, so the motivating example I always use for public key cryptography is the Snowden disclosure of files. Why do we look at Snowden? There's a few reasons. The first is very simple. You are attending a computer science class in what used to be a liberal arts college and now is a little more ambiguous than that, right? One of the expectations of computer science education in this setting is you understand some of the social and political and cultural implications of this content, right? It remains enduringly shocking to me that the Snowden files did not change the world and they affected literally nothing. So that has really impacted my understanding of everything. I saw the content of those files and was oh, the world will never be the same, and nothing changed. The file disclosure happened in 2013. In 2014, I got something that is close to my first real job. I was building weapons for the government at Lockheed Martin, and they had wanted dead or alive posters of Edward Snowden up at the office at work. And I had understood Snowden as a national hero. And so I showed up, and my first job was in that environment. And that caused me to also reflect on the world around me, right? It remained the case at that time until today, my intuitive understanding of the Edward Snowden file disclosures is that he should have gotten a Congressional Medal of Honor. And that was not what happened, right? Then there's also the theoretically and academically interesting case of Edward Snowden, which most people are not famous for understanding cryptography pretty well. There are people that are famous cryptographers. Rivest, Shamer, and Adelson made the RSA algorithm, and so they're household names. The EdDSA algorithm, one person associated with it is named Bernstein, and I know that person's last name because they're part of literal Supreme Court cases, right? So again, there's a political relationship there. Snowden wasn't really a cryptographer. Snowden was an IT person that just understood this stuff well enough and then actually used it for something, right? So that's a little bit unusual. What's the other thing going on with Snowden? Snowden got the files to someone named Glenn Greenwald, who, for those of you that use Twitter recreationally, was one of the best to ever do it on that platform. So I had a strong personal affinity to Glenn Greenwald. This person, I think, picked up a Pulitzer Prize, super highly regarded journalist, and it's just some guy. He was a constitutional attorney before he went into journalism. Very invested in things like free speech, and so on. So Edward Snowden's hanging out, I believe, in Honolulu. And in Honolulu, there's a massive data center operated in some way by the United States federal government. I think it's nominally run by the NSA, but there's I'm sure no one cares about the governmental distinctions there. Why is there a data center in Honolulu? Because very, very close to 100% of internet traffic between the United States and literally Asia, Asia the continent, all of Asia, so I mean Russia, China, Thailand, Philippines, India, probably Saudi Arabia, and some of that stuff will go through Europe the other way, right? But just ludicrous amounts of information flow through this data center, right? And so there's a massive data center in Honolulu, and people working in that data center who are essentially doing surveillance that was like, probably is still widely regarded as being unconstitutional and is carrying on for sure, like, was doing just like massive amounts of digital surveillance of information traffic running across the Atlantic. The perspective of the government at that time was they were not surveilling United States citizens because necessarily that information was leaving the United States. So that was the nominal legal definition for this. Snowden is like, I think, like a libertarian, and so thinks this is weird, because libertarians tend to not like the government surveilling people, I think, is my understanding, wants to do something about it. So Snowden's impression, as was my impression at the time, is that if people figure out about the degree of privacy violations going on in this data center, there will be pressure on Congress to change. And so Snowden tries to invent a way to get this information out that doesn't involve him going to prison for the rest of his life, which is probably what would happen if you disclose this data. Well, I mentioned they had like the wanted dead or alive posters of him, right? So like what he did has been retroactively classified as illegal. Snowden had a problem that I think we can all understand, which is like, I don't personally know any free speech attorneys that also work for the Washington Post personally. So if I needed to disclose information like this, I wouldn't like have a personal friend I can go to, right? I would have to find someone who might do this. And probably the way I find them is by like reading the newspaper, right? So Snowden came to the conclusion that there was a couple candidates to reach out to. And my understanding is Glenn Greenwald was like the first one he got in contact with. So Snowden needs to transmit this like extremely sensitive information that can cause him to go to prison for the rest of his life to a journalist that doesn't know how computers work. And like, that's a little bit of a strong claim, but Greenwald is not a tech reporter or anything like that. So if I'm doing this, I'm probably going to Wired. I'm probably not going to the Washington Post, right? Separately, Edward Snowden's sitting at this data center knowing that every single bit of information that goes out over the internet is being tracked by him and his coworkers. And again, he can't just like pick up a DVD and like throw it off of Honolulu, right? So the information is going over the stuff he knows is being surveilled. So somehow you have to safely transmit something that can cause you to go to prison through the rest of your life directly in front of the people that would send you to prison for it. So how do you get around this problem? Because you can't pick up the phone and say, hey, Glenn Greenwald, configure your Enigma machine to contain these texts, because that phone call is being monitored, right? So this is what is introduced as the key exchange protocol. This is not a supplemental text, this term, but if you're ever interested in cryptography, you can look up this book. It's called The Crypto Book, cryptobook.us. And in this book, cryptographic systems are described in terms of a game for which they solve the problem. So we're going to have something that is called a key exchange protocol. These are things that can happen over the internet that don't look inherently suspicious. So there's going to be a pair of probabilistic machines. What do I mean by that? They're machines that don't deterministically produce a result. So every time I add 2 and 5 together, I always get 7. I need something else. I need a way to generate random numbers. You have seen random numbers. Let's look at the head of length 1 of dev random. So this term, we have previously demonstrated how to generate random numbers as a component of the Wordle assignment. So there's a way to get access to probabilistic information on your machines. So we imagine there are 2 machines, and for the sake of this, we can imagine one of them is a whistleblower and one of them is a journalist. And they are going to take turns transmitting messages to each other. At the end of this sort of transmission taking place, they both have the same value, k. What is the value k? Well, the value k is the secret that they want to transmit. In this case, you can either use this to share a key, to use a shared key protocol, so this is how you can seed your Enigma machine, or whatever you want to do. But somehow you have to start this off and be able to agree on some secret, right? And I don't know why this is here. That completely bamboozled me. The other thing you want to happen is that every time you turn these machines on and start transmitting, you don't want the same information to come out. You don't want to be predictable, because that predictability can be attacked. And then we introduce the notion of an eavesdropping adversary. In the case of Edward Snowden, this was the National Security Administration, right? So even if the National Security Administration can see all of the messages that go back and forth between Snowden and Greenwald, it must be the case that they cannot read the secret content of those messages. They can see the messages are happening. There's no way around that. You can't throw the DVD off of Honolulu, right? But they can't tell what information is being transmitted. They can tell how much, usually, right? So when you start moving terabytes and you work for a data center, it is probably inherently suspicious, but it might not be that bad to move a few bits and bytes here and there, right? So we have someone who is trying to figure out what the secret is, and they can't do it. So we imagine the case, and this is way back in 2013 when people still used hard drives. Do you all remember hard drives before solid-state drives? Your computer would have something inside of it that's spinning, so it would have rotational momentum.
I've taken a few apart.
Yeah. My job before my real job was I made hard drives for a summer. That was great fun. We went out of business basically as soon as I left. So anyways, Snowden has these files, and my understanding is some number of terabytes, so not a comically large amount of information, but the amount of information seems staggering to me in 2013, because there's more bits than I'd ever considered in my life. But at data center scale, quite small. These files are very, very obviously suspicious. So whatever the most suspicious thing you can possibly do on the internet is, think of it that way. They contain keywords. They're attached to someone who is a known libertarian working with high security clearance, right? So very, very suspicious. Absolutely no access to any part of the internet that is not monitored by the United States, but Snowden wants to get some of this information out. So you're going to encrypt some of it in such a way that no one can tell what you are saying. They can tell that you are saying. So how do we carry this out? It is not necessarily illegal or even necessarily suspicious. It has now become suspicious, but it was not considered suspicious in 2013 for people to simply contact journalists. In the case, I think, Oregonian news tips, right? So, if I thought something newsworthy was happening, on this campus, right? If you all did, a cool event or there was a protest going on or something, I would probably not feel bad about calling up the Oregonian newsroom and being hey, there's this cool thing going on in Salem, right? Or maybe I'd be there's this kind of silly thing going on in Salem. We should all go make fun of these students, right? Those are the two things that can happen, right? So someone has to do this, and historically this was protected under freedom of the press and so on. It's yeah, of course, any person can contact a reporter for any reason at any time. That's fine, right? I think. And I'm guessing it's relatively difficult to imagine journalists were viewed differently in 2013 than they are in 2025 in some way that's kind of hard for me to put into words and explain. But the press was viewed differently at that time for whatever reason, right? And it was viewed differently again several years before the Iraq War as well, right? So the way the press has been being viewed at time has changed, and that's a fundamental part of this story. So separately, it's completely reasonable that you might want to communicate something to a journalist that not everyone knows what's going on, because you're allowed to be an anonymous source, right? So I could say hey, there's this thing going on in Salem. Also, please don't say I'm the one that called you. That's fine, because this serves the public interest of if people seeing something newsworthy, they don't want people to show up at their house and ask them what they think about it, right? So that's fine. So we're arguing this is all relatively non-suspicious, and definitely the banks, the big financial institutions, are really invested in people being able to transmit secrets across anything, because they want to be able to see your credit card number to fill out bank transactions, right? So this is not inherently suspicious, though basically as soon as anyone realized Snowden was doing it, it became suspicious, but there wasn't an alarm that went off. So as soon as someone checked what Snowden was doing, it was suspicious. But it wasn't suspicious to see encrypted pieces of information leaving Hawaii, and it wasn't suspicious for anyone to do that in particular. So this is just all nominally above board, and I guess Greenwald says yes after some cajoling from his editor, because he didn't want to talk to a nerd, is allegedly the actual reason that this took so long to happen. So Greenwald, but actually not Glenn Greenwald himself, someone on Greenwald's team who knows how computers work, and I don't know the name of this person, So someone was like, that's like an extremely interesting piece of communication to get, and I understand computers, so I'm going to go help this. So someone goes to Glenn Greenwald's house and like runs a program on his computer that generates a very specific combination of numerical values. Your next assignment is to generate a very suspicious combination of numerical values, right? And one of those values is the thing called the public key, which everyone is allowed to see. And this is a way that if you post your public key publicly, people can take that number, put it in an algorithm that is publicly known, and generate some garbled text that only you can read. Glenn Greenwald is a journalist and is not at all suspicious to be receiving news tips, so he takes that published key and puts it in his Twitter handle, where everyone on Earth can see it, including anyone that simply navigates to Twitter, which is not an inherently suspicious thing to do in 2013. Now, it is very suspicious to go to Twitter now, right? We understand that, right? But it used to be Twitter was cool and people only posted like memes and funny jokes there, right? So anyways, Glenn Greenwald, one of the most prolific Twitter users of all time, just throws this thing in his bio. No one thinks anything of it because, like, of course he would do that, right? Snowden sees this immediately encrypts the payload and sends it directly to him, and it's totally encrypted. Here's a fun fact. So I use iframes sometimes to embed information in my slides. This slide, and so I embedded, I didn't know this wasn't going to work. But this is an iframe of the description of how to contact Glenn Greenwald anonymously, and you can't open it inside an iframe because they're worried about trackers. So we've learned something over time. Here's the link. So, The Intercept is the journalistic outlet that was founded to publish the Snowden files. I don't want to editorialize too much, but I think under 1% of the content of the files has ever been published. And also this site is owned by a billionaire. So, like, I don't know, right? Separately, the second person to ever leak to The Intercept after Snowden is still currently in federal prison. Why am I telling you this? Under absolutely no circumstances should you ever whistleblow and leak to The Intercept. I mentioned I would go to Wired. Just use your critical thinking skills if you need to whistleblow for some reason. And separately, never tell anyone we covered this content in this class ever in your life, because you might later decide you want to be a whistleblower, right? But this is like an academically interesting thing. It's like, hey, we're strongly committed to publishing stories with sensitive material. They're doing their best. They recommend Signal, email's fine. You can do postal. Do not ever send anything in the mail, for the love of God. Like, what are you doing, right? Like, hand deliver a DVD if you have to. What not to do if you want to remain anonymous? So don't do this from school Wi-Fi, right? Like, don't log into this teaching machine using your credentials and then send an anonymous email from it. So anyways, there's a lot of things not to do. But anyways, this is still up, and you can leak any information you want to The Intercept at any time. It's presumably none of us know anything newsworthy, but if you did.
Sorry.
Yeah?
I was just going to say, you need to make sure that you maintain machine anonymity as well.
Yes, so do not do this, okay? Again, the person that did this was one of the best IT professionals working for the NSA in the world and spent years preparing to do it and was still caught almost instantly. And had to hide in an embassy in Hong Kong and get smuggled out by literal Russian intelligence, right? So if you want to do all that stuff, go for it, right? But be ready. Anyways, so I would not drop to The Intercept. I would probably not drop while I'm inside of the borders of the United States. But you should also be aware of one additional story, which is that Reality Winner, 5 years after the original Intercept disclosure, which is now a gazillion years ago, or 4 years later, right? So just a few years, right? Much closer to that event than to now. Released something, and it was either about Russian interference, either the presence or absence of Russian interference, I don't remember. Anyways, this person is in prison forever. In a transitional facility, I don't know. Okay, so be careful. And also, Free Reality Winner, who should be protected by the First Amendment. Okay, so Glenn Greenwald, on his first try, I called him Glenwald, that's not a name, puts the public key on his Twitter handle, and then what else does he do? He has a private key. And the private key is the thing he uses to ungarble the messages that are encrypted using the public key. And he keeps this, we can say on his computer, but that's not really what they do, because Glenn Greenwald has opinions about the United States government and does not trust them. So I think he kept this in like a bomb-proof safe that he was pretty sure the FBI couldn't get into quickly. So yes, it's made on a physical computer, but wherever those physical bits live, it is protected quite strongly. So Greenwald and company, because now there are other people involved, they generate this private key and they protect it zealously. So they didn't write it down on a piece of paper, right? It's in a safe. And my understanding of the safe is there's like some number of hours they think it would take the FBI to get into the safe. And it's like 36 or something. And the thought is someone can flee the country in that amount of time. So anyways, Snowden reaches out to Glenn Greenwald anonymously, and so do like a bunch of other people, right? Because like everyone wants to tell journalists like dirt on their boss, right? So there's a flood of emails that go into Greenwald, and this deluge of emails hides that some of them might be more suspicious than others. So most of them do not come from NSA contractors in Honolulu, right? So people are probably reaching out with stuff that's like not that secret. So the last thing I did, and I didn't like bother doing this anonymously, I found some pretty interesting patterns in policing data like 6 years ago, and I contacted a journalist about them, right? So like journalists are receiving this stuff all the time. And their job is to read it. So the deluge of information comes in, someone on Greenwald's team picks out the sort of diamond in the rough from Snowden. And it's like, oh, we should follow up on this message. Okay, and that was it. That was all they had to do. That was sufficient to transmit large amounts of classified data. Not terabytes, but they were able to transmit enough very secret data in order to set up another protocol for exchanging more information. And then they did escalating layers of security and were able to get this information back and forth. So what are our goals? We can defeat any eavesdropping adversary. Anyone can contact us with any information. We fundamentally have to coordinate somehow, but we can coordinate in plain sight in a way that is not inherently suspicious. And someone that doesn't know how computers work has to be able to like find someone that can explain this to them. And so that is public key cryptography. And from there, we're also going to introduce digital signatures, which is the other application of key generation. So, okay, we're done being Edward Snowden. And now what we're doing is we're buying heroin on Silk Road with Bitcoin, right? So just two objectively moral things that we're doing today, right? I'm sorry, I said heroin, I meant textbooks. So I'm going to buy some textbooks, and not on Silk Road, just on the internet, just like anywhere on the internet. And I happen to have invested in Bitcoin. And again, I didn't invest in Bitcoin because I was planning to do cybercrime. The cybercrime is unrelated to my use of Bitcoin, right? I don't even remember how heroin came up. Did one of you say it? It wasn't me. Okay, so I've got my Bitcoin and I'm using it to buy textbooks because I want to do well in my classes, right? Honest, like I would testify in court that's what I'm doing, yes.
Are these legally acquired textbooks?
How dare you accuse me of piracy? You wound me. So anyways, I've got all these Bitcoins that, again, I don't have from doing crimes, okay? Right. It is not inherently suspicious to have Bitcoins. Lots of people probably have Bitcoins for legal reasons. I think even someone in this class might have a Bitcoin. Everyone look at Teo. Okay.
I don't have a full one.
See, that's exactly what someone who doesn't engage in cybercrime would say, right? Okay, so we're all safe. No one here's done anything wrong ever, right? Okay. How does Bitcoin work? Well, the way Bitcoin works is everyone in the universe knows the whereabouts of every single Bitcoin in the universe. But they know it in this abstract way, where they know a number that is associated with each Bitcoin, and that number represents the current owner. So when someone spends a Bitcoin, what they do is they take their Bitcoin and they hand it to you. You digitally sign it, and then it becomes your Bitcoin. And you digitally sign it in a way that like you had to know who the previous owner is. So we're passing around these Bitcoins by just manipulating numbers, right? So everyone sees every Bitcoin, and they know who the most recent owner is. This is done using a digital signature. So how does this work? Bitcoin Bitcoins are not the same as physical coins. They are evidence of a transaction. So each owner transfers the coin to the next by digitally signing a hash. You know what hashes are? I take a big number, I make it into a little number, right? So I digitally sign a hash of the previous transaction, so whoever previously owned the Bitcoin, and then the public key of the next owner. So someone can verify that the next owner is the person with that public key, right? So that's the key that you put in your Twitter handle, right? And then you add these to the end of the coin. So a coin is basically a series of bits. It's a bit string, okay? So I own a key, or I own a coin. I have a publicly displayed public key that I put in, for example, my Twitter handle, or in the case now, right? So if I were engaging in cybercrime, I would somewhere on this website that I maintain publicly in a high visibility manner for no particular reason, there would be somewhere on this website you could see whatever my key is, right? And for the record, I don't do that. What were we talking about? We were talking about how I don't do cybercrime, right? So I was very busy not doing cybercrime when I posted my key publicly. And then I'm browsing Silk Road, which again is not inherently suspicious and is not illegal, and I see something I really want. And in this case, it's the theoretical Marxist text, the Grundrisse. Does anyone know German and know how to say this? Anyways, it's a copy of this theoretical Marxist text translated to Tolkien's High Elvish, right? Gotta have it, right? Doesn't matter how much it costs. And again, I would like to point out, it is not illegal to buy things on the internet, right? Okay, so I'm just buying something on the internet in a manner that might be legal, right? And so I say, well, I see that someone has this text, and so I say, oh, and I see that person has a public key posted on their Twitter handle, right? And so I take that public key, I jump through all of these hoops, my Bitcoin becomes their Bitcoin, and then they burn this to a DVD, load it into a trebuchet, and fire it from Honolulu to my doorstep, or like however they transmit the information to me.
When did that take place?
Sorry?
Like what year did that take place?
What year did what take place?
The transaction.
Outside of the statute of limitations.
Okay.
So like a long time ago. I don't have any Bitcoins. How dare you?
No, okay, that's scarce.
No, I don't do cybercrime.
All right.
I keep all of my crimes veganic, locally sourced, small batch, artisanal, right? When I want some crime, I just go commit a felony, right? Like I don't know all these people that are using Bitcoins, right? And for the record, I have never committed a felony because I've never wanted to do crime. Okay, I feel like I'm getting a lot of unusual questions today. See, this is why people don't teach politically relevant content, right? Because people start asking you why you know so much about how to do crimes. It's because it's my research area. Okay. So, when I'm busy not doing my crimes, and again, these are the crimes that I don't do, someone needs to verify that I am spending my coins that I required legitimately, regardless of whether it was legally, so just legitimately, we say, and they want to verify that it is me spending the money. So I'm going to write down the transaction details. I'm going to say, hello, my name is Professor Calvin Deutsch, I'm an assistant professor of computer science, Willamette University, and then I'll get a call from legal, and they'll say, you can't list Willamette University as your affiliation. And I'll say, like, a small private liberal arts college in the Pacific Northwest. And I am purchasing a copy of the Quenya High Elvish theoretical Marxist text, the Grundrisse, which you should all read. I found it in the library the other day. That's why it's the example. And someone's like, wow, that is so wordy. What are you doing, going for a minimum word count? What do you think this is, an English class, right? And so I say, not to worry, it's not an English class. I just wrote an SHA hashing algorithm, so I'm going to hash that message I sent you. And then there will only be 256 bits of information, no matter how many I started with. And then I will take that hash message, and I will get up my secret encryption machine, and I will put the hash of the message in one side, and I will put my private key in the other side, and it will spit out a message that only I could have encrypted in that manner, but which everyone with my public key can decrypt to see what I was saying. The general public, which is you all, who have no vested interest in proving that I engage in cybercrimes, will of course see this message, and you'll say, ah, here's a message here. It appears to say, or some garbled text, right? And here is Calvin's Twitter handle, which has in its bio a public key. I can take that public key and put it in one side of my cryptographic algorithm, and I can take the gibberish and put it inside the other. and it will spit out an SHA-256 hash of the original text, which will also just look like gibberish. But if I have also seen a document that is claiming to be the original text, I can verify that it has the same hash. So you can perform the same integrity transaction we did on saying, hey, do I have an actual copy of Ubuntu? You can say, hey, do I have an actual message that could produce this hash? And it's very unlikely to get that hash by accident, right? So if someone has what they claim to be a message from me, and they can verify that it has the correct hash, then they can be highly confident, but not absolutely certain, but certain to, like, it is beyond the realm of mathematical possibility this happens coincidentally, right? It's 1 over 2 to the 256, which is a very large number. Then they say, oh, okay, I can be highly confident that this is the message it claims to be. This is what it looks like to me conceptually. Is that too small? Can I even make it bigger? No. Okay. I have an unencrypted transaction. I take the message, and I take my private key, and I create a ciphertext of the message. This becomes an encrypted transaction, which can be released as a ciphertext out into the world. Anyone who has access to my public key and the public ledger of the ciphertexts can take that message, perform a simple mathematical operation on it. This is the RSA example, but it doesn't matter what the mathematical operation is. And they can get a decrypted transaction and verify that I spent my Bitcoin. And from there, we are now going to introduce Edwards' digital signature algorithm. And we are going to do that not today, but we are going to do that next time. Thank you for joining me today. I hope you learned something about anything.